Hi and welcome back. So in the past video I was trying to work out this math problem, and essentially what we're trying to do, and let me actually I should write this down. What we're trying to figure out is we're trying to figure out what the mass of our nucleus is, or what percentage of the mass of an atom is contained in the nucleus. So essentially I've set up this fraction here. And essentially what this is we've got the mass of our nucleus, which is we've got 2 protons and 2 neutrons. So we've got our protons are blue and our neutrons are purple. And so we've got the mass of our nucleus on the top of our fraction, and then the mass of the entire atom on the bottom of the fraction. And so this should give us a ratio of how much mass is contained in the nucleus versus how much is contained in the entire atom. And in the last video, I was trying to plug this into my standard calculator that came with the computer. And I guess this I'll probably make a video about this in the future, where this calculator that I have really isn't built to handle I guess, or it really doesn't handle scientific notation all that well. It handles it with this this exponential notation button, and it was still kind of giving me trouble. So this could maybe turn into a bit of a learning opportunity, and I could tell you, if you don't already know, that Google can be used as a calculator. So I actually plugged this expression. So I've got our numerator of our fraction plugged into Google, and Google found out that the value of our numerator is going to be 6.694 times 10 to the 24th is going to be the value of our numerator. So I'm actually going to go ahead and write that down. So this is, I'll give myself some more space. So the value of our fraction is going to be 6.694 times 10 to the minus 24th, and that's actually going to be grams. That's the mass of our nucleus. That's just the mass of the nucleus. Let me just make sure I wrote that down correctly. Yep, I think I did. And so now we're going to take that, now we're going to figure out the mass of our of the denominator, which is going to be the mass of the entire atom. So we're going to add to this, going to add 2 times 9.109 times 10 raised to the minus 28 power. So this is what this last term is that I've got highlighted, where I've got 2 times 9.109 times 10 raised to the 28th power. This is going to be the mass of our 2 electrons inside of our helium atom. And this is going to give us the mass for our denominator is going to be 6.6958. Let's write that down. So this is going to be 6.6958 times 10 to the minus 24. So we have 6.6958 times 10 to the minus 24 grams. And now you can see we've just got a simple fraction. So we've got two terms. They're something times 10 to the minus 24th. So actually these will both cancel, and so will, I guess, the units. Our grams will cancel, so we'll just be left with a simple fraction. And now this is something we can just plug into our standard calculator. So now let's just figure out. So all I've got now is I've got the mass of our nucleus, which is the numerator of this fraction, over the mass of the entire atom, which is the denominator of this fraction. So let's figure out just how much, what's the ratio. So we plug in 6.694 divided by 6.6958. And there we go. And we could multiply this by times 100. So this will give us the percent, and we can see that 99.97% of the mass of our atom is located in the nucleus. So this means that, I'll just write this down, that inside this helium atom, where I said that most of the mass is inside this nucleus. When I say most of the mass, we've now figured out that most of the mass is 99.97%. And that's inside something that takes up only 1/10,000th of the space of the entire atom. So that's interesting, right? You know, we've got this atom that is mainly empty space because it's all this space that's taken up by these two tiny electrons, and it's just that they're moving around so rapidly, and they're you can't even necessarily localize them and say that they're definitely going to be at this spot or they're definitely moving at this velocity. But the probability of where they are takes up so much space, and all the mass of the atom is taken up inside of this nucleus, inside this thing that is 1/10,000th of the space of the entire atom. So, that's interesting. You can imagine that, if, I know when I was a kid, there was this movie called Honey, I Shrunk the Kids, which I don't know how old you are if you're watching this video, but I remember part of that. The plot of that movie was Rick Moranis' character invents this ray gun that essentially shrinks down different objects, and he was saying that basically because, and sort of the premise of the movie was because you have these atoms are mainly empty space, that only 1/10,000th of them, and I guess that's not counting the actual size of these electrons, but they're still negligible. But 1/10,000th of essentially all atoms really is empty space. So what they theorized in that movie was that you could shrink something down 10,000 times. But then you should imagine, if we could shrink down something 10,000 times, and maybe I'll actually do a specific example of this, and maybe the next couple of videos, where if we had something, or if you had one human hair that was solid nuclei, nuclei of atoms that had no empty space, seeing as how we have 99.97% of the mass of an atom in this thing that's really, really small inside of an atom, if you had even just a human hair that was solid nuclei, you could imagine how much that would weigh. You would have like a human hair that weighed 10,000 pounds or something like that. And even I'll try to, maybe in the next video we'll do an example like that. But maybe this video was really just intended to show you specifically how much of the mass is actually located inside the nucleus of the atom. So anyway, in the next video, I might do something like that. But also, we've got more stuff to cover. I have to still cover, I still haven't introduced you to the periodic table. I still haven't defined what the atomic mass unit is. So anyway, in the next video, or in the next bunch of videos, I'll maybe cover some of those concepts. So anyway, thanks so much for watching, and I'll see you soon.